yesterday we saw something about current mirrors and how both using bipolar transistors as well as MOSFETs one could obtain what are known as current mirrors. In fact, application of current mirrors you will just begin to realize when we discuss further about analog integrated circuits. Now, today we will continue where we left. In fact, there are certain modifications of the basic current mirror that become very useful in certain cases. These are minor modifications, that is why yesterday we did not discuss. Let us consider the basic current mirror here. The diode is biased by means of a reference current, whatever it is, which is supposed to get reflected exactly as I naught. There is a problem here in making I naught very close to I reference because of the fact that I naught divided by beta and I naught divided by beta, these base currents have to be supplied obviously by reference itself. That means, this reference has to supply these base currents, which is twice I naught by beta. So, that has to come out of I reference, then only the collector current is going to be supplied. All the collector currents are exactly identical, that is assured, there is no doubt about it, because all the transistors are identical. But our attempt is to make this collector current as nearly same as I reference. So, in that attempt we can also adopt what is called current amplifier. Why go for feedback and all that? We have abundant current amplifiers at our command. What is it? Current amplifier is nothing but the transistor itself. Instead of supplying this current directly from I reference, I would rather supply the base current of a current amplifier and make the emitter current supply the base currents of these two. So, this is still equal to I naught, this is I naught by beta. Now, this emitter current is going to be twice I naught by beta and this current is going to be twice I naught by beta divided by beta plus 1. So, to that extent the burden on I reference is reduced. So, this is another technique, a minor technique of using a current amplifier within this current mirror, so as to make this I naught very close to this. So, now this is nothing but twice I naught divided by beta into beta plus 1. So, I reference is going to be very close to this. Next, is this clear? How this is a commonly used current mirror. Only difference between this current mirror and that current mirror is in terms of reverse bias here. What is the reverse bias of this transistor now? This is no longer a diode connected transistor, but a transistor itself, because it has a reverse bias of V gamma. Okay. And therefore, if you want current reflection to be exact, you would like to have the collector potential of this with reference to ground to be at 2 V gamma, that you have to remember. That means, if this is going to supply to maybe next stage, you would rather use a Darlington pair. Now, it looks similar to this reverse bias. So, the current mirror is exact. So, this is the next stage. If ever you use this kind of current mirror, then this is one way of interconnecting the next stage to it. We will come across this later in our op amp circuit. Is this point clear?
Does the match necessarily that?
Not necessarily, if it is possible, otherwise there will be a certain amount of mismatch because of early effect. Pardon?
Base current.
Base current for this.
Yeah.
Yeah, it has to come from this, right. This will be the structure here. So, this is going to be having this and this. So, this is a similarity between this structure and this structure. So, if this current mirror is going to act as some load, let us say, then this is the next stage amplifier. Okay. Now, another minor variation of this, which we had not discussed in yesterday's class, was what is called as emitter degeneration. That is, why not put resistances in the emitter? What will happen if you put resistances in the emitter? Output impedance will shoot up, because this is nothing but current sensing. Output current is sensed and fed back as a voltage. So, this is similar to the Wilson current mirror that we had discussed, where output current is sensed and fed back as a current. Okay. Here output current is sensed, fed back as a voltage here. So, emitter degeneration also causes improvement in output impedance. Output impedance of this structure will go towards 1 over HOB, from 1 over HOE. So, exactly similar situation exists here, that the output impedance improves, and advantages. Disadvantage, of course, this kind of thing is not recommended in IC design, particularly because we are shy of using resistors in ICs. So, but there is an advantage here. Okay, you can now make the two resistances equal if you want the current to be equal. If they are different, the currents will be determined by ratio of resistors. You have V gamma here and V gamma here. So, IE1 into RE1 is equal to IE2 into RE2. Actually speaking, so IE2 into RE2 is equal to IE1 into RE1. So, you have the current ratios determined by resistor ratio. So, apart from improving the output impedance, the emitter degeneration resistor causes also you to choose the current ratio the way you want. So, current ratio can be made different from 1 based on the resistor ratios RE2 by RE. Okay. Now, this is a further degenerate version of the same circuit. One end emitter resistance is removed altogether. What good is this? This is a very important current mirror called Widlar current mirror. What does it do? Let us see. This is the output current and this is the reference current. We had already established that I reference and I naught are related by a very important relationship, in the sense, if this is VBE1, let us say this is T1 and this is T2, if this is VBE1, what will be the value of VBE1 in terms of I reference? VBE1 VT log I ref by IE naught. This is known to us. Yesterday we had seen how this relationship is used in obtaining what is called as translinear principle. So, I reference is Vt log I that is VBE1 is equal to Vt log I reference by IE naught. VBE2 similarly is equal to, please tell me what is VBE2 in terms of I naught? VBE2 is Vt log I naught by IE naught. So, what is VBE1 minus VBE2? That is the voltage across the resistance Re. So, what is equal to VBE1 minus VBE2, which is the voltage across Re, which should be equal to I naught into Re. I naught into Re is the voltage across Re, that is equal to Vt log I naught by. It's an important relationship. The voltage across the resistance Re is I naught Re is equal to Vt log I naught by I reference. Of course, this is a nonlinear equation which you have to solve in order to obtain value of I naught, but this is not the way IC designer is going to view it. IC designer wants to have an I naught which is very low compared to I reference. I reference may be of the order of milliamperes, which could be easily obtained by using voltages of the order of tens of volts and resistors of the order of kilo ohms. We have already seen that our transistor ICs do not prefer large valued resistors. In order to therefore develop low valued current for biasing, we cannot use resistances of the order of mega ohms. So, in this particular case, without using resistances of the order of mega ohms, using only resistances of the order of kilo ohms, we are going to design a circuit for low valued currents. Let us see how. Suppose you have 1 milliampere as I reference and you are required to get I naught, which is 1 by 1000th of it. That means, you are attempting to get a current of microamperes. Normally, you should have used mega ohm resistance. So, we already know in a design I naught by I reference as being equal to 1000. So, you know this is 1000. So, Vt log 1000, Vt is 26 millivolts at room temperature. So, 26 millivolts log of 1000, natural log of 1000 divided by Re or divided by I naught will give you the value of Re required to be put in order to get I naught of 1 microampere. So, straight away the design is very simple, straightforward. Is that clear? So, we have the voltage here 25 log 1000 divided by I naught will give you the value of the resistance mostly in kilo ohms range. This is clear, I suppose. This is again commonly used in all situations where I would like to generate a low valued current from a large valued current as the reference.
But sir, instead of going for a resistance, we can scale the transistor sizes.
Yeah, we are coming to that. We will come into that when we discuss further about translinear principle. Let us see, as he points out, let us see a situation here, whereas I connect one transistor like this, the current is going to be I naught. Suppose I connect another transistor like this, current will be again I naught. N number of transistors, and I parallel all of them, I can get n times I naught as the output current. So, getting a current which is a multiple of what? The original reference current is no problem, because I can parallel current sources, but parallel current sources technology wise means what? Collector is, all collectors are connected, all bases are connected, all emitters are connected. That means, area of the transistor is what? Double the original area if 2 transistors are connected. If 3 transistors are connected, triple, like that. Therefore, multiplying the whole thing, the area by area, you can generate currents which are going to be ratio of areas. Is this clear now? It is not necessary to have integral multiples. The ratios can be shown to be ratio of areas, and you can have the current as ratio. The disadvantage of such a scheme is what? The output impedance is progressively decreasing. As you shunt the current sources, output impedance is going to progressively decrease. Okay. So, we will again see this particular principle reflected more efficiently in what is called translinear principle. Okay. So, making the currents different by means of areas is another. The current can be only multiplied. You can generate a current which is higher than the original current. Now, these other current mirrors are current mirrors which are MOSFET versions, like these NPN versions. We can have MOSFET version, but the only warning is that the MOSFET should be not depletion mode, it has to be enhancement mode. Only then I can connect what? Gate and drain and still have a current source. The transistor will be operating in the current saturation region. So, for that purpose all current mirrors make use of enhancement mode of MOSFET in realization. As far as JFET is concerned, again JFET is basically depletion type of this thing. You cannot have a current mirror using JFET. JFET you can only have current source of the type we discussed yesterday, wherein we are just going to short the gate and source. If you want a different current in this case, or if you want higher output impedance for this current source, what can you have? Like emitter degeneration, you can have source degeneration resistance put here, and therefore you can get what will be the output impedance of this structure now? The current can be made different depending upon RS. What will happen to the output impedance? Do you remember this? If the original output impedance is RDS, what happens to the output impedance when there is source degeneration? 1 RDS into 1 plus, by how much will it improve? RDS into 1 plus GM into RS. This is what we had discussed in basic electronic courses. This output impedance will be RDS into 1 plus GM RS. So, please work out this problem as a homework problem, that show that the output impedance of this JFET current source when there is a degeneration resistance of RS is equal to RDS into 1. The same principle is used in improving the output impedance of the current mirrors using MOSFET here. Here that this is nothing but what is called as cascode current mirror. This we had discussed yesterday using bipolar transistors. We had seen that in such a situation output impedance is going to increase, go towards 1 over HOB. So, similarly in this case output impedance is again going to increase. Originally it is RDS, it is going to increase by 1 plus GM into RDS. So, this is how the output impedance of this is going to improve by a huge factor, and therefore, this is another current mirror in the case of MOSFET. This is nothing but Wilson current mirror drawn. It is exactly similar to the Wilson current mirror we discussed yesterday, that is using current feedback. Again in this case output impedance is going to improve. For all these cases I would request you to work out the output impedance in terms of the FET parameters. Please do this as a homework problem. Work out the output impedances of all these current mirrors in terms of the FET and the transistor parameters. So, yesterday we were exposed to the translinear principle. Let us try to understand what this translinear. What trans here means is transconductance which is linear with respect to current or voltage. Transconductance which is linear with respect to current or voltage is what we are talking about. Let us see what can be the devices that can have transconductance linear with respect to voltage or current. This is some basic principle. I mean, I want you to just think of this as a synthesis procedure. Suppose you are asked to call for a device which requires to be translinear. What should be the relationship between current and voltage? That is how we will put. So, current is a function of voltage. I want delta I divided by delta V. This is input current, this is output current versus input voltage. I want delta II by delta I naught by delta Vi, which is called the transconductance. Transfer output current and input voltage. This is the transfer that has taken from input to output. The transconductance should be linear with respect to what? Current. So, transconductance should be linear with respect to output current. This is one thing. Another way is transconductance should be linear with respect to output input voltage. These are the two things possible. So, what does it mean? Delta I naught by delta Vi is equal to K I naught, or delta I naught by I naught is equal to K times delta Vi. What is this? Solve this. What do you get? Log or I naught is equal to exponent K times Vi, right. This is another K0. This is what is required of the functional relationship between current and voltage. The device should have this. I am not bothered about what device that is. Basic requirement is this, from that I am starting. Okay. So, it says it shall have this kind of exponential relationship. Look at this. Now, you will be pleasantly surprised. This delta I naught is equal to K Vi into delta Vi. So, I naught is equal to K Vi squared. So, fortunately God has decided it should be complete. Our world will be complete with two devices that you require. What do you require? It shall be linear with respect to voltage. It shall be linear with respect to current. What? Transconductance. And God has created these devices, not man. Is this clear? So that the entire thing is complete. Man has to only search for such a thing, okay, and he has found it out. That one is nothing but bipolar, another is nothing but field effector. See how complete it is. So, it is not that we got these devices and then realized, it is complete. It is required. In our innermost mind, we had this requirement and we were searching for it and we got it. This is what is meant by translinear principle. Okay? That means both are translinear devices. And therefore, what is it that we can do mathematically with this principle of translinearity? Lot of things in signal processing. That is all about analog signal processing. Let us see. We just said that when we connect equal number of diodes or base to emitter junctions in clockwise direction as well as anti-clockwise direction in order to form a loop. They can be connected in any random fashion, but there should be equal number of diodes both in clockwise direction as well as anti-clockwise direction. Why is this requirement of equal number of diodes? Why should there be that requirement? If it is not equal, what happens? Kirchhoff's law will still be satisfied, there is no doubt about it. Just can you think of, in our expression for these things, we had IE naught coming at the denominator. Those will not cancel, and the entire purpose of our signal processing gets lost. It becomes device dependent. So, this is the reason for having equal number of transistors or diodes in clockwise direction and anti-clockwise direction, forming a loop, and therefore, this is now formed into a loop, and therefore, we set pi, that is times I, let us say I is equal to 1 to yam, okay, divided by I E naught. Okay. This is equal to I E naught to the power, actually it will have I E naught to the power yam, actually speaking, and then this is in the clockwise direction, this is in the counter clockwise direction. I j is equal to 1 to yam. It is because of this requirement of cancellation that we require these numbers to be the same. Well, let us see a minor variation. Here, what is I E naught in terms of current density? J E naught. J E naught is the basic parameter of the IC. Okay, current density, because current density into area is what gives the current. So, I can split this in as I E naught as J E naught times, okay, A I. Is this clear? J E naught to the power, yeah. Here this will be again J E naught to the power m into A j. Is this clearly understood? Now, obviously, J E naughts are same, that is why we have put it as J E naught to the power m, and they can be cancelled. And this is the most generalized translinear principle relationship, that the current densities, product of current densities of those transistors or diodes connected in clockwise direction shall be equal to the product of current densities of those transistors or diodes connected in the anti-clockwise direction, counterclockwise direction. Now, again we are coming back to this. If you are using just 2 diodes or 1 diode, what happens? That is nothing but the current mirror. So, you will have, let us say, I reference divided by A reference equal to I naught by A naught, or I naught is equal to A naught by A reference. So, we have shown what we have earlier indicated using circuits. We had seen this current mirror, okay, wherein we had paralleled the current sources and shown that it is ratio of areas, but here now mathematically we have indicated clearly it can be made a fraction or any number you want. Therefore, this is a technique of obtaining different current ratios by using different areas for the devices. Is this clear? Okay. So, this is part of the current mirror aspect, but we are trying to extend this principle to more general things. Let us see very exciting signal processing circuits now. Consider this first circuit. you can just do this without the help of paper or pencil. Just looking at the circuit you can obtain it. These are the two diodes connected in one direction, these are the other two diodes. What are the currents in this? Ix, Ix. So, Ix squared shall be equal to this diode carries IU and that is I naught, IU into I naught. So, therefore, I naught is equal to Is square by IU. So, this is a simple operation of squaring. If Ix is your signal current and IU is the reference current, just you are squaring the current. This kind of signal operation is required when you want to find out RMS value of a given waveform or anything. So, you have to square and then integrate and find out the square root. So, these simple operations can be straight away done with the help of these translinear principle. Look at the dynamic range of this is fantastic, that is the whole thing. This relationship, the translinear relationship is the only known relationship in electronics which is valid over what kind of range? Several decades of variations of this current, that is starting all the way from microamperes, it can go up to tens of milliamperes without any problem. This relationship is valid. So, that is the unique property of the bipolar transistor. That is the only device which can handle current in that dynamic range, not voltage, but current. So, this relationship is a God given relationship which is to be exploited fully.
But the FETs is a problem.
FETs, there is no such relationship. Exponential is basically data compression. Okay? Exponential relationship simply means data compression, squaring has nothing to do with it. Okay. So, that is why bipolar device is more popular device signal processing wise than the FET. Even in the FET you are looking for subthreshold region of operation where the operational relationship is exponential. So, people are trying to use FETs in the subthreshold region where the relationship is exponential. Okay. Now, let us see this interesting circuit. Ix can be bipolar. What I mean is it can be of any direction, it can go in or come out. When it goes in, this transistor does not take that current, this is the only transistor which is connected as a diode that takes that current, then this diode is getting a reference of Ix into it. Now, this is a current mirror. So, Ix is going to flow through this, no problem. That is, for a current flowing in this direction, Ix will be reflected here by the current mirror. Is this point understood? Now, what happens when the current is in the opposite direction? That is not permitted by this diode, it cannot take that current can be only taken by this, if this is biased properly. What do you mean by biased properly? The bias voltage should be nothing but 2 diode drop. Okay. If that is 2 diode drop, okay, this is going to conduct properly, it should be just let us say less than 2 diode drop. So, that when this is conducting, this is okay, basically off. So, this is going to conduct and this is going to carry a current in this direction, okay, in the opposite direction, and therefore, we have in either direction we have this circuit operating, and therefore, IW is nothing but magnitude of the current.
So, there is a problem in biasing the DB putting there because the load, I mean the load voltage is going to determine again what VB should be.
Which one? Here, this is only a bias voltage. Okay. Current is injected from this by means of a current source. Okay. So, the bias is going to be only for making the base to emitter junction conduct. Let us consider this circuit. Ix, this looks like a differential stage, but you can see Ix is going to flow through these two diodes. So, Ix squared okay. This let us call it I1, this has I2, this is nothing but IW. So, Ix squared is equal to, please tell me, I1 into I1 plus I2. You see that I1 plus I2 flows through this. Ix squared is nothing but I1 is the current flowing in this transistor into the current flowing in this transistor, which is I1 plus I2. Is it clear? Next, Iy squared similarly is nothing but I2 into I1 plus I2. So, Ix squared I1 plus I2 okay, is nothing but I1 plus I2 is nothing but IW. So, let us see, I1 plus I2 is according to that nothing but Ix squared by, what is it? I1 plus I2 is nothing but, you just add these two, just please add these two, I1 plus I2 into I2 okay, plus, what is it? I1 plus I2 into I2, that is nothing but, no, you just add these two, Ix squared plus Iy squared I1 into I1 plus I2, that is nothing but I1 plus I2 whole square is equal to Ix square plus Iy square. I1 plus I2 is therefore nothing but Iw, which is root of Ix square. This is an important circuit. This is Ix and Iy are the two inputs, and output will be a current which is root of Ix squared plus Iy squared. What is it? Vector magnitude. So, this is a very neat circuit. You can see just using transistors and diodes I am able to obtain a very complicated signal processing formula, which is nothing but vector magnitude, Ix root of Ix squared plus Iy squared. Next, this one. This is basically a simple circuit which we can also formulate very simply. If I connect two diodes in clockwise direction and two diodes in anti-clockwise direction, then the currents in I1 and I2 in two diodes will be equal to, product of currents will be equal to I3 into I4. That basic principle can be used for multiplication, division, everything. Okay. So, you can formulate large number of such 4 diode loops, and all of those 4 diode loops will become multiplier circuits. So, one such technique of multiplication is this. Let us see. You can see that this plus this is going to be equal to this plus this, correct. So, this is Iy, this is Ix. So, Ix into Iy is equal to Iw into Iu. Iu could be the reference current. If Ix and Iy are the signal currents, it is a multiplier. If you make I y as reference I u and this as signal, it becomes a divider. Okay. So, you can use this is nothing but basic technique of multiplication adopted by exploiting the principle of log antilog relationship that is inherent in the bipolar transistor. Is it clear? So, we can therefore see that this property has been used in all modulators, modulators and demodulator circuits ICs are nothing but multiplier circuits, and we have a variety of multipliers ICs generated only using this principle of 4 diodes, 2 of the diodes in one direction, 2 other diodes in the opposite direction, forming a loop. We will see this property as well as the property of the differential amplifier in converting the input voltage into a functional relationship between the input voltage and output current in the next class. Okay. So, the differential amplifier as a basic building block is nothing but 2 diodes connected in opposite direction. If you apply voltage, it will convert it into some nonlinear function. If I apply current inputs, we saw that current inputs which are going into diodes, it can become a multiplier, right. So, this basic cell which is called as Gilbert gain cell, that is what we are going to discuss later. This is nothing but 2 transistors connected like this, okay, and again 2 transistors, further transistors or diodes connected like this. These diodes are also transistors. Right? So, that means actually speaking, now you will have all these current sources coming in. Please assume these things automatically, that current input should forward bias the diodes. Okay. So, in such a situation, the current into the current in this, okay, multiplied by current in this, these are in the same direction, is nothing but current in this multiplied by current in this. So, you can just look at the circuit and arrive at the solution if you know the translinear principle. Okay. So, we will further learn about the use of this translinear principle in current mode operation of circuits in the next class. Thank you.